Spotify. We are a company, in case you didn't know, that we do streaming music. We stream things from data centers where we have somewhere roughly around 3,000 servers. We distribute somewhere around 12 soccer fields of music. That is, if you would record the music onto cassettes and spread them out on the floor, that they would cover an area of roughly 12 soccer fields. We stream about 4 Wikipedias of bandwidth per second. And according to our latest official numbers, we have something like 24 million people who use it. And those numbers are either completely pathetic or kind of impressive, depending on if you've ever worked for Google or not. Okay, so the Spotify backend, which is all I care about, being a backend engineer, consists of somewhere around 70 services. It's kind of hard to differentiate. Sometimes you have like one service that is actually running, well, one code base which turns into multiple services and so on, but somewhere in that vicinity. And we're trying to keep each service responsible for one small task, to have them separate and replaceable and so on, and in order for people to be able to work independently of each other, which has worked out pretty nicely for us. Back when Spotify started and we didn't have 24 million active users, we were pretty much exclusively a Postgres shop. Postgres is a really, really awesome project. It has very many very nice properties, including a very nice price tag. But once you get up to a certain scale, Postgres has some problems. Perhaps the biggest one for us is cross-site replication. If you have many data centers all around the world and really crappy internet connections connecting them, where really crappy internet connection basically means anything where you're not running your own fiber optic cable from one data center to the next one, then Postgres is going to hurt you a lot occasionally. The way Postgres does streaming is that so long as everything is fine and dandy, it will just send live updates, and the lag for Postgres will just be a second or two and everything will work pretty nicely. But when something hits the fan, it will basically start rsynching big chunks of files, and it will have a very hard time catching up if you're still doing writes, and everything will just keep sucking worse and worse, and you will need manual intervention, and someone will be woken up in the middle of the night, and that really kind of gets boring the 4th time it happens in the same month. So another more obvious problem with Postgres is that you can have write masters and hot standbys and things like that, but to get good security, you will pretty much need manual intervention if your write master dies. So that's also a problem. And of course, in order to scale to big data with Postgres, you will likely end up having to do sharding, and once you do sharding, pretty much all of those nice database features like transactions, atomicity, relations, all of that just goes out the window. So then using a relational database kind of becomes pointless. Okay, so we use Cassandra for some services, and why would you use it? Well, like I kind of hinted before, if you can use a relational database of some kind, by all means you should. And if you can't, that usually is because you have some kind of really, well, what's usually called big data. We have this fancy pretentious quote here about big data is data that exceeds the processing capacity of conventional database systems. The data is too big, moves too fast, or doesn't fit the structure of your database architectures. Blah, blah, blah. Yeah, probably if you have these problems, you know about them, so I don't need to tell you any more about them.
So what is too big in that context? How big is too big in an absolute sense?
So the question was, what is too big? Usually you will know it when you see it, because you simply cannot scale anymore. And that is very much a moving target, because hardware keeps getting better and better. A few years ago, we didn't really have anything better than rotating Rust to store bits on, and these days we have these really awesome Fusion IO SSD things that don't even use SATA and can do 500,000 operations per second. So basically, it's a moving target. I'm sorry, I did not actually answer your question, but there is no true answer, so you're just going to have to live with that.
I'll try.
Okay, so a bunch of things about Cassandra. It does not support a relational model. It's basically a key value store. We'll talk a little bit more about that later. In order for you to extract anything approaching reasonable performance from Cassandra over the long term, you will need a pretty deep understanding of all of the components, all of the algorithms, and so on. So it's really very far from a turnkey solution. There is no support for complex transactions. It's just a few years old, so it's kind of immature, which will bite you again and again if you end up using it. And data analysis is a bit tricky. With us in our audience here, we have a guy called Elias, and he's really awesome with everything approaching data analysis. He will be speaking after me, so I will not be talking anything more about data analysis in Cassandra, because he would just correct me, and that would be humiliating. Anyway, so what does Cassandra provide then? Because that was kind of a big list of nice things to have that Cassandra doesn't. So, like I said before, it's basically a key value store, but in two levels. So you give a key, and what you gain back is a key to value mapping. And you can also do slice ranges, so that you can say, I want everything from key 9 to 28 or whatever, and then you will get an ordered set of keys. And that's pretty much the API for Cassandra. I'm not going to talk a lot about Cassandra internals. I will mostly focus here on how we use Cassandra. So if you're not really following all of those technical tidbits, just consider them line noise. My wife does that anyway. So every time you do a request to Cassandra, whether it's a read or a write, you can specify what kind of consistency level you want. That is, how sure do I have to be about reading or writing the correct data? Most of you guys are hopefully in a technical background, and you know the CAP theorem, where you have consistency, availability, and persistence, and you can only pick two, and that is pretty much always true. But in the case of Cassandra, you really can choose between the C and the A, which one of them you really want. So, another nice thing about Cassandra, no single point of failure. We actually upgraded our database cluster from one of our largest Cassandra services recently. We just switched out 60 nodes and replaced them with much cooler and much more expensive hardware on a running service without a single second of downtime, and I think that's kind of cool. Also, the write performance is really fantastic. You pretty much cannot, you can pretty much approach the speed of whatever's underlying storage you're using. It will batch things up, and it will be very, very quick. The read performance, it's so-so, but the read performance depends very strongly on your write patterns, and it can be very tricky to analyze, and it can deteriorate over time and so on. So it's not really all that awesome, but it can be made to work. All right, so I'm going to go through one use case here about how we used Cassandra. It is for our playlist. No, wait, that's the next slide. So, wait, first. Yeah, we started using Cassandra 2 years ago, and we have about a dozen services that use it. And like I said before, we don't think of it as just a black box that we can store things in. You really need to look at it as a utility toolbox of algorithms that you can configure how you want to use, and you need to know what you're doing with every one of them, or you will lose a finger. There are all of these fancy features in Cassandra, like CQL, which is kind of like SQL, where I think SQL is one of the few reasons to stay away from relational databases, so I'm not really a big fan of CQL either. There are a bunch of other things like secondary indices called supercolumns and so on. We don't use any of that because it tends to be immature, it tends to be buggy, it tends to not scale to our levels, so we kind of tend to stay conservative. If you have smaller data sets, then you can probably use them just fine, but if you have smaller data sets, then you can probably use Postgres, and you should. Anyhow, I was talking about playlists before. So our playlist subsystem has roughly 1 billion playlists, and that amounts to about 22 terabytes of compressed data. Cassandra automatically compresses things if you ask it to, and then it's 22 terabytes. We serve about 40,000 requests per second from a cluster of 60 nodes. So that's reasonably big. Once again, unless you're Google, in which case it's pathetic and yada yada yada. Basically the way we do playlists is we want to support really advanced offline things because that's super cool. So you can actually have 2 or 3 different clients that you all go offline with, and then you can edit the same playlist in all of these clients. And then once you go online again, all of those changes will be merged into one seamless history without any user intervention or anything. Why? Because this is a really fun problem to solve. It's probably used by like 1 ppm of our entire user base, so 24 people or something. But anyway, it's there and it's kind of interesting and cool. So if you start to think about it, what it basically amounts to is a distributed version control system with lots and lots of commits. And these, well, people here are familiar with distributed version systems like Git, right? Yes, awesome. So basically Spotify playlists are Git repos. And we store a bunch of changes, like patches, and some other things that are just there to make things go quickly. And it turns out that Cassandra is actually pretty neat for storing this kind of data, because we get you know what the hash ID of a patch set is, right? So if you want to read a patch set, you can just say, give me this patch set. And in Cassandra you have something called a consistency level, which means you can decide how many nodes you want to read from. And if you just read from the one node, you might sometimes get the wrong data, or in this case, no data. But since we never overwrite any data, if we know that the data is there, we can just do a read from one node, and either we get the data and everything is fine, or we can retry it and read from more nodes, and we will know that we will get it then. But since we never override any data, we can usually just read from one node, so we will get good performance, which is kind of cool. So this is a web interface rendering of how a playlist looks. We can see that we have a bunch of changes, and we have here a split where someone went offline and did edits to the playlist from 2 different places. And this is the representation of this changelog in the Cassandra database. We have one line here, and we have one column per commit where the column ID is sorted, so it's a numerical value. And then we have a protobuf thing containing the operations and the parent pointer, so that we can get a linked list of how things are all connected. If you're not familiar with Protobuf, it's a serialization format, kind of like JSON or whatever, but you have slightly higher efficiency, and you have templates for how valid messages look, so you can do some kind of validation and stuff like that. The next part of our storage is something called head. And this is very much like the head in Git. Naming is not really an accident. It's just a column family that is in non-Cassandra speak, what one would call a table containing the link to the head of the version pinging.